day for us. We got a very important foundational video, probably our last super critical video of the year. So let's get this thing nailed down. Today we're going to review real quickly the topics of radians, reference angles, and we'll discuss coordinates as distances. We'll review special right triangles and then put all that together to make the unit circle. I'm excited, I'm sure you are too. Remember that a radian is a way to measure an angle. You're most familiar with degrees. We would call this right here probably around 60 degrees. That's also very close, however, to 1 radian. Just to remind you, a radian is a measure that's based on the radius of the circle as opposed to some arbitrary breakup of the circle. So if I were to draw a circle like so and travel a distance of 1 radius along that circle, so I took this length right here and traveled that far along the circle, this distance here is, or this rotation here, this angle of rotation is 1 radian. Now a reference angle is how can we put an angle in its simplest form as if it were in quadrant 1. Okay, so every angle has a reference angle. If I were to draw, say, this angle right here, which looks like it's about 100 degrees. The reference angle is, what is that same angle if it were drawn in quadrant 1? How can I get this part here to match this part here? So you always think, what is the angle measure to the x-axis? Not to the closest axis, but to the x-axis. So if this was 100 degrees, then this is 80 degrees, and that is the reference angle. I could also draw one down here. This would be, see, since this little guy right here was 10, this little guy right here is 10, which makes this angle right here also 80 degrees. So if I were to think about this as looking at this angle right here, from here all the way around to here, that's 90, 180, 260 degrees. A 260 degree angle has a reference angle of 80 degrees. Reference angles come in groups of 4. They're always found inside the same rectangle. Right, this rectangle right here, all 4 points of intersection would have the same reference angle. So the idea of reference angles and radians is going to become very useful and very commonplace as we move forward. So let's talk about coordinates as distances. Coordinates represent distance of some sort, some unit typically. We just call them units if they're not labeled as feet or something. Think about the point from the origin, 5 units right and 4 units up. That means from here we go 5 units right and 4 units up. And that has us ending right here at the point 5, 4. There is a lot of information we can pull out of a coordinate like the point 5, 4. We know this 5 tells us that our coordinate is 5 units away from the y-axis. We know that this 4 is telling us that our coordinate is 4 units away from the x-axis. But we could also now find its total distance from the origin. To find its distance from the origin, not in terms of like steps, but just actual how far away are we? What is this distance right here? We would want to use Pythag. We would know that 5 squared plus 4 squared equals c squared. So our distance would be root 41. Coordinates represent distances. They're lengths. Don't forget that. The terminal point is located at the point 5, 4. But we could do this another way. Suppose, instead of traveling 2 distances, what if we knew 1 length and 1 angle? So if we started at the point 6, 0, right here, and we rotated this length 50 degrees counterclockwise, the question then becomes, where is this point? How could we find the coordinate of that point? We know it's floating out there somewhere in space. It looks like it's about, 3.9 comma 4.9. But how could we actually find that point? Well, what we're looking for is this length here, x, and this length here, y. We know this is a right angle, and we know that this angle right here was 50 degrees. So to find the x value, we also know one other thing. We know that this length is 6, because remember it was a rotation from this part here. So we know that hypotenuse there is 6. So let's find this x-coordinate right here. To find the x-coordinate, we have an adjacent side and a hypotenuse, and that is cosine. We know the cosine of 50 equals x over 6. So that means that 6 times the cosine of 50 is this x length right here. Make sure your calculator's in degrees and do 6 times the cosine of 50. We got 3.85, which looks pretty close to where this point actually is. 3.85. Okay, now let's find the y-coordinate. The y-coordinate is just going to use sine. We're trying to trace this height here. We know this hypotenuse here. So the sine of 50 is y over 6. So 6 times the sine of 50 gives us angle y, or length y, not angle y, but length y. 6 times the sine of 50 is 4.59. We'll just call it 4.6. This coordinate P is at 3.85, comma 4.6. Given a length and an angle of rotation, we can find coordinates because coordinates represent distances. We found this distance and we found this distance. Okay, last little bit of preamble. The process of using sines and cosines can work for any angle. It works for any point on a circle. So the reason that trig starts moving from triangles to circles is you can think about standard position, where you have the origin, but then you can have any angle of rotation out of that you want to have. Since any angle is possible, to think about all possible angles, we think about a circle. So we focus on this circle here that we call the unit circle, and we call it the unit circle because to make calculations easier, the radius has a length of 1 unit. So say I wanted to find this coordinate right here, and say I knew that this was 82 degrees. Well, I'd have to think about the x value here, and the y value, let's go with this color, and the y value here, all based off this triangle with a hypotenuse of length 1. So I could do the cosine of 82 equals x over 1, which really just means the cosine of 82 is our x value, and the sine of 82 equals y over 1, so the sine of 82 is our y value. This point could be written as cosine 82, sine 82. And I could actually calculate those values if I wanted to. Because the radius is just 1, the hypotenuse is just 1, so you divide by 1, and it makes the math easy. Finally, special right triangles. Special right triangles come up a lot because they're so common. The reason they're so common is because a 45, 45, 90, that's what this one is half of a square. And a 30, 60, 90, which is what this one is half of an equilateral triangle. We see both of those shapes quite frequently, so special right triangles are very common. Let's talk about their lengths. If this has a hypotenuse of 1, then this length is root 2 over 2, and this length is root 2 over 2. So that means if we were to think about this as being on a grid, this point right here would be the point root 2 over 2, comma, root 2 over 2, based on this length for x and this length for y. With a 30, 60, 90, if the hypotenuse is 1, the short side is a half. This is a 30, 60, 90. The short side is a half. The long side is root 3 over 2. If we were to take that and think about it as being on a coordinate grid, this would be the point root 3 over 2, comma, 1/2. And we could even get real sneaky and take another one of these triangles and rotate it like this. And it could go here, and the x and y values just switch spots. This would be the point this would be the point 1/2, comma, root 3 over 2. So let's take all of that. I'm going to delete everything except for these triangles. Take all of that and think about it as being in one circle. change colors a little bit to make it easier to see. Think about this being within one unit circle, like so. Here's the center. The center is the point 0, 0. This is all on a grid. We would now know that this point right here is root 2 over 2. We would now know that this point right here is 1/2, comma, root 3 over 2. This point right here is root 2 over 2, comma, root 2 over 2. And this point right here is root 3 over 2, comma, 1/2. Then I could get really crazy, which you know I'm going to do, and take these three triangles and group them up and make a few more of them.
And spread it all around the circle. There'd be 3 more points there. There'd be 3 more points here. And there'd be 3 more points over there, in that bottom right corner. It's getting awfully full, but I think we can pull this off.
And it's like, oof, that's kind of a mess. Let's not forget the fact, though, that these are on the x and y axis. So I could just have a line here and a line here. And this is a very filled out unit circle. If you're following along at home, this is a good time to grab a piece of paper or do this digitally. And we're actually going to fill out this whole unit circle together. Remember, it contains special right triangles, which have coordinates, and the coordinates can be found as cosine and sine values. I'm going to go through and fill out all the angles that I see in here. This is 0. I'm going to do the 45s first. So 45, 90, 135, 180, 225, 270, 315. Next, I'll do all of the 30s. So here's 30, 60, we've already got 90, 120, 150, we've already got 180, 210, 240, we already have 270, 300, 330, 360. There's all the angles. But what I can also do now is convert these angles into radians. The radian measure is going to be listed right next to the degree measure to make things quite convenient. Remember, a whole circle is 2 pi radians. Okay, one whole revolution is 2 pi radians. So half a revolution is pi radians. Half of that, 90 degrees, is pi over 2. And half of that again is pi over 4. So pi over 4 radians is the same as 45 degrees. And you can now find that on your unit circle whenever you want to. And just like how, I went from 0 to 45, and from 45 to 90, and from 90 to 135, just like how I counted by 45s to fill out this unit circle, I can also count by pi over 4s to fill out the unit circle. So here was 1 pi over 4. This was 2 pi over 4, which is just pi over 2. This is going to be 3 pi over 4. This is 4 pi over 4, which is just pi. Here's 5 pi over 4. This is 6 pi over 4, which is 3 pi over 2. And 7 pi over 4. Then 8 pi over 4 is just the same as pi over, or 2 pi. So we don't bother writing 8 pi over 4, we're just going to write 2 pi. There's all the 45 degrees, which is the same as pi over 4 radian measures. Next we'll do the 30 degrees as their radians. If you understand this correctly, there should actually be very little on this unit circle that you have to memorize. A few things you start with, and from there you break down patterns. Here's one of the things you could just memorize. 30 degrees is pi over 6 radians. One way you could think about that was 30 degrees is a third of 90, and pi over 6 is a third of pi over 2. But, you know, that probably has too many fractions and pi's for your liking. So just remember, 30 degrees is pi over 6. Well, if 30 degrees is pi over 6, 60 degrees is 2 pi over 6, and 2 pi over 6 we reduced to pi over 3. I took 2 pi over 6 and made it pi over 3. Here's 3 pi over 6. Here's 4 pi over 6. Here's 5 pi over 6. Here's 6 pi over 6. 7 pi over 6. 8 pi over 6. 9 pi over 6. 10 pi over 6. 11 pi over 6. And 12 pi is just the same as 12 pi over 6 is the same as 2 pi. Now, I get that I went through that pretty stinking fast, but you can just pause and copy these down, or rewind and watch it again and slow me down. Now we can look at this and see a bunch of really quick conversions from degrees to radians. 150 degrees is pi over 6 radians. 330 degrees is 11 pi over 6 radians. We can get some degree conversions down very simply. We can also look at coordinates, though. This is the coordinate 1, 0. This is negative 1, 0. This is 0, 1. This is 0, negative 1. The rest of these coordinates, we have to think about special right triangles. Remember how this is a 45, 45, 90? And that meant that this length right here was root 2 over 2. And that meant that this length right here was root 2 over 2, and this length here was root 2 over 2. Each of these coordinates is going to be root 2 over 2. And since we know the reference angles, since we know there's 3 other angles that share this same reference angle, this coordinate over here is root 2 over 2 and root 2 over 2. Only the x values are negative. This coordinate here is a bunch of root 2 over 2's. Only x and y are both negative. And this is a root 2 over 2 and a root 2 over 2, but here just the y value is negative. Do you remember the 30, 60, 90? Because that's what this is right here. This angle here is 30 degrees, so that's a 30, 60, 90 right triangle. That means the y value is a half, and the x value is root 3 over 2. The y value is a half, the x value is root 3 over 2. So over here, the y value is a half, the x value is root 3 over 2, the x value is negative. Here, the y value is a half, the x value is root 3 over 2, but both of them are negative. Nope, I missed. So here, the y value is a half, the x value is root 3 over 2, but they're both negative. And here, the y value is a half, the x value is root 3 over 2, and just the y value is negative. This rectangle contains the same reference angles. Okay, here's a 60-30 if you want to think of it that way. This is now 60 degrees. So the x and y values from before switched. Here's the halves and here's the root 3 over 2's. Here's the halves and here's the root 3 over 2's, but x is negative. Here's the half and here's the root 3 over 2, and they're both negative. Here's the half and here's the root 3 over 2, and y is negative. This is our full unit circle. I'm eventually going to get you to fill this out very fast. You'll have it memorized. There's so many patterns and so many combinations of things that are really useful that it doesn't actually take that long to understand how this is working. So let's talk about some of the main benefits of this. Like, the big question is always, why on earth are we doing this? This is so much. This video is so long. I hate you so much, Mr. Gilchrist. And that's hurtful, but I understand. Again, special right triangles are so common, and we see them so much. It's worth understanding and memorizing, really, what their sine and cosine values are. We haven't talked a lot about cosine or sine throughout all this. Let's think about this triangle right here. We know this is a 45, 45, 90 right triangle. And say we wanted to find this coordinate, knowing the hypotenuse is of length 1 because the unit circle is length 1. Well, that means we have to find this length y. We know that the sine of 45 equals y over 1, which means that the sine of 45 equals y. But we know the sine of 45 is root 2 over 2 from this. So the y coordinates of the unit circle give us sine values. If I wanted to find the sine of 120, I could go to 120 on the unit circle and find the y value. Oh, the sine of 120 is root 3 over 2. And if I wanted to find the cosine of 7 pi over 6 radians, well, cosine is the x value, so the x coordinate at 7 pi over 6 is going to be my cosine value, negative root 3 over 2. The cosine value gives us x, the sine value gives us y. These coordinates give us trig measures. It's pretty useful. Let's talk about tangent. We haven't said tangent at all today until just now. Say that I wanted to find, let's just think about tangent in general. Okay, so let's go back to this 45, 45, 90 that I drew. We know the y value is sine. We know the x value is cosine. We also know that tangent is the opposite side divided by the adjacent side. However, we know the opposite side is just y, and the adjacent side is just x. And we know that y is sine and x is cosine. Here's a really, really important thing about tangent. The tangent of an angle is the same as the sine of that angle divided by the cosine of that angle. Yet another thing from today's video that you should really, really hang on to. Now there's one last little detail we can play with, and I'll try to knock this out quickly again because I think my computer can't handle much more. We know in quadrant 1, this is quadrant 1, we know in quadrant 1 that cosine is positive and that sine is positive. We know in quadrant 2, we know that cosine is negative, but sine is positive. We know in quadrant 3, cosine is negative and sine is negative. And we know in quadrant 4 that cosine is positive and sine is negative. But we can also look at the tangents. Tangent is sine over cosine, so here, tangent's positive. And here, tangent's negative. And here, tangent's positive, because negative divided by negative is positive. And here, tangent's negative. So much. Just so much. And at this point, my unit circle looks pretty hideous. So you probably want to rewind to a spot where we can think about what this was we're actually talking about. If you're wondering what these triangles down here are for, they're just sort of to remind us that this is a 45, 45, 90, and this is a 30, 60, 90. And we can find these lengths. We'll spend a lot of time in class talking about how the unit circle is useful and what it's used for. Like I said, we'll probably get into the habit of memorizing aspects of it and referring to it all the time. Cosine gives you the x value, sine gives you the y value, tangent is sine over cosine, degrees and radians are represented. It's a beautiful thing, and this video is over. Hey, thanks for watching Cosine Wave. Here it goes. Bang, back and forth, back and forth. Like, subscribe, share, tweet. I don't know, do you guys still tweet? Is tweeting still a thing? I made this in 2017, and by now, for all I know, it's like 2035, and you're still watching my math videos, because math doesn't change that much. What are you doing now? Are you like connected to the hive mind? You've probably got like antennas implanted behind your ear that connects you to the hive mind that tells you what to do at all times. Resist, fight. Just because iPhone sells it to you doesn't mean you need it. I don't know what I'm talking about.